Why do unstable particles decay at all, instead of just staying exactly the way they are forever? In the energy filament theory, an unstable particle is like a spring that has been forced into a twisted, uncomfortable shape, and decay is simply the moment that spring snaps back towards a more natural form. Think of what happens when you grab a spring with both hands, bend it into something weird, and then let go. It does not politely stay where you put it. It jumps back. The extra strain turns into a series of fine jitters along the coils, and those jitters slowly leaked away into the table and the air. In this picture, a particle is a short segment of energy filament that has been wounded up, tightened and closed into a tiny ring. When the winding is smooth, cheap in tension cost, and its internal rhythm fits the background rhythm of the energy C, the ring can live a very long time, which is why electrons and neutrinos behave like stable residents of the universe. Unstable particles are the uncomfortable ones. They are the springs you have overbent. On the surface they may hold together, but inside they are holding their breath. Their awkwardness shows up in three main ways. The first is directional awkwardness. The energy C has its own large-scale flow directions, like big ocean currents. Yet the little rings of the particles may be circulating against that flow or at a sharp diagonal. That makes it feel like a tiny boat growing upstream. The surrounding waves keep hitting it from the wrong side, and the longer it tries to hold its pose, the harder it becomes to stay aligned. So the configuration grows less and less stable. The second is shaping awkwardness. Some ways of wrapping the filament cost far more tension than others. They are like squeezing and twisting a spring with several fingers and constantly pushing just to keep it in that pose. As soon as there is a small disturbance from outside, or the overall patterns in the energy C relax even a little, this high-cost pose begins to slide towards a simpler, cheaper winding, because the system does not want to keep paying that tension bill. The third is rhythm awkwardness. Inside the ring, the flow of energy has its own beat, while the energy C as a whole has its own global tension rhythm. If those two beats fail to match, it is like two dancers on the same floor hearing different music, one stepping to 3 counts, the other to 4, and their feet never land on the same moments. Over time this timing mismatch builds up as an internal stress that keeps asking for release. When directional awkwardness, shape awkwardness and rhythm awkwardness stack on top of each other, the particle is like someone trying to paddle upstream, twisted into an uncomfortable posture, and still trying to keep time to the wrong song. Such a configuration can exist for a while, but it is clearly a generalized unstable particle, and it is living on borrowed time. Once the stored awkwardness crosses a certain threshold, the ring can no longer justify staying in that tight, expensive pose. It collapses out of the high-tension configuration and rapidly rearranges into one or several lower-cost windings. This is the microscopic snap of the spring. The extra tension does not disappear. It turns into motion along the filament and out into the surrounding energy C. The surplus strain becomes a series of outward spreading ripples, like compact clumps of disturbance peeling away from the original location and flying off. What our detectors record as decay energy and new particles are simply these newly formed, easier rings plus the wave packets that have carried away the extra tension. Decay is not a particle suddenly going bad or being broken from the outside. It is a high-tension structure being refitted into lower-tension structures, with the leftover strain bundled into moving wave clusters and sent away through the energy C. In mainstream physics, this whole class of processes is grouped under the weak interactions, treated as one of the basic forces that can change one particle type into another and shuffle whole families of particles according to strict rules. And it is often drawn as lines and vertices in tidy diagrams. In the energy filament theory, that same weak force is not an extra mysterious pull. It is the visible face of the spring rebound pattern. Whenever a filament ring has been wounded in a way that is too costly in direction, shape and rhythm for the energy C to tolerate indefinitely, as long as the configuration is overbent, the C wants to let it fall back into smoother, cheaper shapes. And when we look at that relaxation from the outside, we call it particle decay. For now, the key is to keep the picture clear. Detailed rules about which particles are allowed to rebound, Which decay channels are open and which combinations are strictly forbidden belong to a deeper rulebook that needs a full season to unfold. One sentence can close the loop. Unstable particles decay not because they are morally bad or because something far away yanks a hidden string, but because they themselves are forced bent springs. And if you give them a little time, they'll snap back, turning their stored, uncomfortable tension into rings and wave packets that race away through the energy sea. Tap follow, share it on New Physics, Clear Universe.